This system resistance seminar is brought to you by the John Brooks Company. We have been providing fluid handling solutions to the Canadian marketplace since 1938. Our products include pumps, spray nozzles, filtration equipment, and valves. Plus, our custom engineered systems provide fluid handling solutions for a variety of industrial and municipal applications. In this presentation, we will be discussing pumping system resistance curves, or more commonly known as system curves. First, we must ask, what is a system curve and why is it crucial in achieving a successful pumping application? A system curve represents the total resistance a pump must overcome in order to develop a range of flow rates through a specific piping system. This resistance is made up of both static and dynamic values. Let's first build a simple piping system. Now fill it with fluid. The static portion of the resistance is the pressure exerted by the column of fluid's weight. If we put a gauge at the bottom of this column, it will register the pressure being exerted by the weight of the fluid above. Keep in mind, the density of the fluid will affect the pressure gauge reading. This static pressure reading is not dependent on the pipe diameter nor orientation. All that matters is the vertical height of the fluid. Filled up to the same level, all these pipe systems will register the same static pressure. Let's now consider friction, or the dynamic portion of the resistance. Friction resists the motion of the fluid as it passes through the piping system. The amount of the resistance due to the friction depends on a few factors. 1. The roughness of the interior pipe wall. 2. The length of the pipe. 3. The velocity of the fluid traveling inside the pipe. And finally, the viscosity of the fluid itself. As a reminder, viscosity is a measure of a fluid's resistance to flow. Besides straight pipe, other components usually make up systems, such as elbows, valves, filters, etc. All these components have their own specific friction loss values, which can be obtained from their respective suppliers. Let's put a pump in the system and feed it with liquid from a large tank. Since the system is full, the gauge is reading the static pressure. Once the fluid starts to flow, there is an additional dynamic resistance due to friction. This adds to the static resistance already being shown on the pressure gauge. Note, for this example, we will neglect any friction loss or static head on the suction side of the pump. In fact, let's just take it out of the picture completely and install a flow meter. Next, we will create a graph that shows the flow rate along the horizontal and the pressure gauge reading on the vertical. We will now measure the amount of flow being pumped and graph this value against the total resistance shown on the pressure gauge. Don't forget to plot the static head against zero flow. If we spin the pump shaft faster, more flow will be generated through the piping system, increasing the friction. We will plot this new flow rate against the new value shown on the pressure gauge. Let's continue to increase the speed of the pump and plot the corresponding flow rate and pressure gauge readings. Smoothly connecting these plotted points creates a system curve. It represents all the possible resistances between 0 and this largest flow rate in our unique piping system. Let's go back to our piping system from before. Here was the system curve we plotted. If we now open the manual for the pump, we will find the pump curve information. There will likely be at least two sets of curves, one with constant impeller diameter and changing pump speed, and the other with changing impeller diameter and constant pump speed. Let's now lay the system curve over both sets of pump curves. If, say, we wanted this certain flow rate through the pumping system, we could either keep the impeller diameter constant and run the pump at this speed, or keep the speed constant and use this impeller diameter. Let's go back and revisit the original piping system. If you recall, we generated the system curve by running the pump at different speeds and then we recorded the corresponding flow and pressure gauge reading. In reality, we don't have this luxury. We usually have to select the correct pump for a specific flow in advance of the piping system being built. So the system curve has to be generated mathematically. We will address this topic in the next presentation. This concludes part 1 of our system curve presentation. Please contact us if you have any questions or would like to attend one of our pump hydraulic seminars. John Brooks is dedicated to the fluid handling market with specific solutions to your pumping, filtering, and spraying needs.